So this talk will be relatively beginner's talk. So I'll start from the beginning about C++ fuzz testing, and then I'll talk about how to integrate it into the CI/CD, which I think is a relatively new topic and wasn't discussed a lot. Let's get into this. Another note, all the concepts that I'll be talking about here are general concepts. They're not connected to any like third-party tool. When I started working on how to integrate fuzz testing into the CI/CD, I started a company named Fuzzing, which helps actually integrating the fuzz testing into the CI/CD in various ways. Recently, it was acquired by GitLab. So at the end, I'll show a preview of now it's a GitLab capability, but I'll also talk about open source solution that you can use as well, and general concepts. Yeah, so a little bit about myself. So the last company that I did was acquired by GitLab just about, I think, a few weeks ago, actually. Before that, I did a lot of security research, also a few cybersecurity startups here in Israel. And before that, served at the cybersecurity part at IDF. Okay, so what we'll talk today about. So we'll talk today about what is fuzzing, what types of fuzzers exist. Then we will focus about libfuzzer, which is kind of the de facto standard, maybe libfuzzer, AFL, and for C++, it's part of Clang, which is very convenient. And then we'll talk about how it works, about a little bit about the internals of libfuzzer, and then we'll move to continuous fuzzing and how to integrate those kind of new tests into the CI/CD, because the workload of fuzz testing is significantly different from standard unit tests, and they introduce new challenges of running them in the CI/CD, just like you run unit tests. So we'll talk about those challenges and possible solutions. Then we'll discuss case studies, trophies. Then we'll discuss also what fuzzing does not replace, because sometimes what it does not replace and what it does not solve. So it solves some things, but it doesn't solve everything. So we'll talk about this, the future of fuzzing, and then I'll show a short demo, a preview of GitLab capability, then we'll do Q&A and discussion. Okay. So what is fuzzing? So fuzzing is actually providing semi-random input in an automated way to a program in order to uncover bugs and crashes. The next question that usually people ask is it only to find security, memory corruption vulnerabilities? The answer is, in C++, usually yes. The main concern is memory corruption and vulnerabilities, which lead to a lot of serious vulnerabilities that we read about, especially in unsafe language like C++. But actually, fuzzing was also introduced into many safe languages like Golang, because you can also find stability issues, and you even can find logic bugs and logic security bugs. So we'll talk about that, how to find logic bugs in your C++ code, and not only memory corruption bugs like heap overflow, Stack Overflow, etc. So, and essentially, fuzzing is a way to run millions of unit tests without actually writing them, which is, I think, pretty cool. Okay, so quick history about and types of fuzzers. So we have traditional, which are called random fuzzers, and they just generate completely random input and try to find bugs in the program. So usually it's not very effective, because to find crashes, you have to find one specific input out of kind of infinite number of inputs, and the probability to find this input is very low for traditional fuzzers. And I think about maybe 10 years ago, or AFL introduced a new way to do that pretty effectively, using coverage guided. And coverage guide, I'll talk about how coverage guided fuzzers work, but essentially they're instrumenting the program, and they're using feedback they're using the coverage feedback, to understand if the input that they generated was good enough, and then they can use this feedback to generate smarter input to get to new coverage, and then find new bugs quicker. And I'll talk exactly how this algorithm works. So really, AFL was kind of the first one to do it in a very large scale. There were also some papers before AFL, but AFL was kind of the industry leading tool to find a lot of security issues in a lot of very famous libraries. Then we have LibFuzzer. All of them are kind of the same algorithms, more or less. And the nice thing about LibFuzzer for developers is that they actually, from Ceiling 6.0, this is built in. I'll talk also about some of the nice features in AFL that are not available in LibFuzzer, but for developers, I think from my experience, LibFuzzer is really the easiest to use because it's available built in Ceiling. And it was ported also to safe languages, to GoFuzz by Dmitry Vyukov. Rust is CargoFuzz, but actually it's based on LibFuzzer. And then there are some JQF is Java, JSFuzz, Python Fuzz, and Java Fuzz. They are ported from GoFuzz by myself, so you can have a look at them as well. Okay, so let's go through a very simple example of how coverage guided fuzzing works. So as I said, it's a beginner's talk, and then we might dive to more advanced topics, but I want to go through really the basics stuff of how coverage guided fuzzers work. So let's say we have a parse complex function here that gets an input, and what the function actually wanted to do is to test the string, to test the byte, the character array, and if it gets the characters fuzzed, it wanted to return true, otherwise return false. The problem is that actually there is a bug here. There is an classic off by one, actually an error that probably everyone did in their development in their lifetime, and probably will do more. So there is an off by one, and actually if it gets the word fuzzed, it will crash because it will access an out of bound array. So let's go to the next slide. 1 second. Yeah. So before I show you how to write a fuzz test, I want to go through high-level description of how coverage-guided fuzzing works. So on the left side, we can see how random and traditional fuzzer works. So it just generates completely random input each time, and then it executes the input. And if it found the bug, then great, it will save the input. If not, it will just generate another random input. So in coverage guided, on the right side, we have one preliminary step. We instrument the program for code coverage using usually standard code coverage library. Then for infinite for loop, we choose a random input from something called the corpus, which is introduced in a coverage guided fuzzers. A corpus essentially is just a directory with test cases. If the directory is input, then it just generates a new random input. Then it mutates the input, and I'll talk about some of the mutations. And then it executes the input and collect coverage. And then it is doing another test. If this test cases got us to new coverage, so got us to new code passes that we didn't hit before, we added to the corpus, to this directory. So this way, every time we hit new code coverage, we add the interesting test cases to this directory. So actually, it's also a good way to increase coverage without writing with writing just one fuzz test and not writing thousands of unit tests. But I'll talk about that as well. So this is really very high level description of how coverage guided fuzzing algorithm works, and it is called also generational algorithm because the fuzzer generates a better mutation every time. So if it hits new code coverage, so if we hit new code coverage, this is a good thing, and this is a better mutation, a better test case, we save it into the directory. If we don't hit new coverage, the mutation is not good enough, and we just ignore it and try to generate to take another test case from the directory and mutate, and hopefully get to more code coverage. So now I want to show you how to write a very simple fuzz test with libfuzzer for the previous function that we saw. So you can ignore the package parser here. It's a typo, but you have to implement a function that is called LLVM fuzzer test1 input. I know the name is a bit long, but this is what the C-lang libfuzzer developers chose. So you implement this function, and this function will be called essentially infinitely by the libfuzzer engine, and it will pass the pseudo-random data to the data variable and the length to the size variable. And then you have to call the function that you want actually to test, which is in our case is parse complex. We pass data and size. So how we compile this, C-lang plus. I used C-lang 8, but it will work. Yeah, sorry. So it can work with any C-lang from 6 and up. if you have clang which is less than clang 6, then I think it's also possible to add libfuzzer, because libfuzzer was also available just as standalone binary, so you can link with libfuzzer. I believe you can find documentation of this on the internet pretty easily. So if you have clang which is bigger than 6.0, you add the flags fsanitize equal fuzzer, and this will link it with libfuzzer. And then you add the sanitizers. I'll talk about sanitizers later, but here I used the address sanitizer, which will help us find the heap overflow in that case. Okay, the memory corruption, and then we just pass it to the parse complex, and the parse complex, the fuzz parse complex CPP. So parse complex is the function that we is the file that contains the function that we want to fuzz, and fuzz parser complex is the file that contains this LLV and fuzzer test1 input function, which is essentially the main function for libfuzzer. If we are running it, and then we can run the libfuzzer binary, it will find the crash in about 3 seconds, which is pretty nice, because if we would try to use a standard traditional fuzzer, probably it won't find the crash. It will never find the crash, because really the probability of finding one sequence of bytes is 0 out of all the possible sequence of bytes. I want you to, I want you to talk a little bit more about the under the hood of the of how coverage guided fuzzers works, and specifically libfuzzer. So on the left, just as I said, every time the traditional fuzzer will just generate random, completely random string, or actually a byte array, character array, and it will never hit the word fuzz it, right? Because the probability is really 0. On the right side, it's not all the byte arrays that are being generated, but this is all the test cases that are actually saved in the corpus. So this is all the mutations that are better than the old mutation and are being saved to this corpus, to this directory. So in the beginning, we will just add an empty string, which gets us to, of course, it gets us to new coverage, because before that the coverage was 0. And the next one will be f and let's say something like 4 A's. It gets us to new coverage because if you remember, I'll go back to the function. So every time how the test cases that are generated and saved to the corpus looks like, every time it discovers another new character. So this is why the test cases that are saved look the way that I showed you before. So every time it discovers a new correct character, that gets it to another code coverage. So every if here is instrumented. Every condition in this if statement is instrumented, and it gets us to new code coverage. And every time we hit a new correct character, we save it to the test directory, and then we hit the correct sequence of bytes, and we have the memory corruption crash. Yeah, so I think really it started like fuzz testing AFL and fuzzer started from the idea of finding memory corruption vulnerabilities, because usually they lead to serious security issues, and AFL really found thousands of bugs, as well as, and then fuzzer of security related bugs that were some of them were exploitable, and some of them probably like bad actors also used fuzzers to find them, and white hat hackers also used them to find those and fix the vulnerabilities. But it's not the only thing that we can do with fuzz testing. We can actually also use it to find logic bugs that can lead just to incorrect software, and sometimes logic bug also can lead to security issues. So for example, if we have if you are writing a classic example is let's say a JSON parser or a YAML parser or any other parser in CCPP, then we can use a libfuzzer to automatically find us logic bugs that happens. For example, we know that we need to find something that is always true. So for example, if we call encode on the data and then we decode it again, then it should so it should be equal to the same data, right? This is a basic standard property of an encoder or any encoder decoder library. So this is why it's called property-based fuzz testing. So we want to find the property which is always true. So in this case, we know that encoding and decoding the data should leave the data intact, or we should get the same data. So we compare, in this case, we compare the data that we got from the fuzzer and the data that we got from encoding and decoding using our library. And libfuzzer will help us find any combination of data that that actually it will help us find any combination of data that doesn't that fails this assumption, and this will be of course a bug or a logic bug. Yeah, so and this is also why it is very useful in not only in unsafe languages like C++, but also in safe languages like Golang and Rust, etc. Okay, so yes, this is trophies of AFL. I believe some of you saw this page. There are really thousands of security issues that were found by AFL and libfuzzer, and there are other fuzzers as well, other fuzzing engines like Fuzz, and I believe there are even more which I'm not aware of, some more like homemade fuzzers. Yeah, so another important step in the mutations, which I showed you earlier. Yeah, so another important step in the coverage guided algorithm is the mutations. So mutations is what we do every time we take a test case from our corpus, from the directory. Then we need to do some mutations on this test case, and hopefully this will get us to a better test case. So it will not always get us to a better test case, but in some cases it will get us to a better test case, and we'll save it to the corpus as well. So what are those mutations? So in AFL, the author of AFL, I think the correct name is Mikhail Zalwitsky. I'm not sure if I pronounce it correctly, so sorry about that. He also worked at, I think he worked in Google while he published this the AFL tool. And the mutations that he introduced that were very effective, at least for some libraries that were doing parsing of network protocols, parsing of JSON parsers and other libraries as well, are bit flipping. So just taking random bits from the test cases that are in the corpus and flipping them, doing AND with changing bits, changing byte flipping is just taking random bytes from the test case and doing AND with other random bytes. So this will essentially flip, ending with a byte that is all XORing with a byte which is all ones. So it will flip all the values for this specific byte that was chosen randomly. Some arithmetics, like adding big numbers, adding another byte at the end. So we make for example, we can make the sequence longer, and we add some, it's called like magic bytes. Actually, I'll share the screen later, and if you look at the algorithm in like AFL, libfuzzer, or gofuzz, it's a huge if statement where each statement is each case is one of the possible mutations. A lot of them contains magic bytes and magic numbers, but it really proved to be very effective. So there are a lot of like magic numbers like max int or max short. So a lot of magic numbers that are known to cause like out of bound array and other stuff. So a lot of that is really heuristics, but it proved to be very, very effective. There is another thing that is called, I think, sonar, but the word sonar, I think, was introduced actually in gofuzz, but libfuzzer is doing also something similar. When compiling the target, it actually can take also some constants and strings from the target itself. So this way, it actually reuses some of the strings and bytes and constants that are available in the target to generate the sequence as well, which is pretty cool. Okay, so solutions and what fuzzing is not. So it does not replace unit tests, which are usually quick and they check very basic behavior. They does not replace integration tests or I would say any other tests. What they do replace is, I think if you have if you used traditional like fuzzer, just a random fuzzer, probably you can switch and use coverage guided, as there is no, I believe there is no advantage to traditional fuzzer on coverage guided fuzzer that uses instrumentation and coverage feedback, or if you had some kind of test that really looked like copy paste of tests, trying to find crashes or incorrect behavior. Probably you also might be you would be able to use fuzzing instead. And if you didn't use fuzzing and you have some C++ code which is accessible in some way to the outside world, and is doing some kind of parsing, or even not parsing, but it's accessible to the outside world, and it's security critical because it runs either on your servers or on someone's like on mobile, doesn't matter. It's really very good practice, especially in C++, to have at least some fuzz testing, because C++ is really very vulnerable to those kind of memory corruption vulnerabilities, which really leads to a lot of security issues. And if you don't introduce fuzz testing yourself, and for the developer, it's actually easier than for the hacker, because the developer has the available source, and he knows his code better than the hacker, so he knows where to write the fuzz tests and which function he should fuzz pretty easily. Then what will happen is a black hat hacker, or the bad guys, they will use fuzz testing as well. Maybe not effective as you would do, but still it will find the crashes, and then your software will be exploitable. But of course, it's not. I wouldn't say you should use fuzz testing for every software. It really depends on what your software is doing, but really, if it's doing any kind of parsing, or if it's accessible to the outside world, it's a production software, and it's running on your internal servers, parsing some images, or if you're running parsing software on mobile, then you should really think about introducing fuzz testing to your code. Yes. And another thing that fuzzing does not replace is secure design and like threat modeling, attack surface reduction. Really, if you use fuzz testing, it doesn't mean that there are no more bugs. It just means that you found some bugs. Your software improved. You found bugs before the bad guys found them, and but it doesn't say that no more bugs are available, because fuzzing, it's not a magic software just finds all the bugs in your software. It's very good in finding some bugs in your software. So you need to think about the secure design. You need to think about what happens if there is a bug. How do I reduce the attack surface, and really any other security best practices. So this is not talk about security best practices, but just in one note that it does not replace other security best practices. Okay, so continuous fuzzing. Yeah, a second. Yeah, so running a fuzzer once is nice, and will find you bugs. But just like you run your unit tests, every time you push new code, you also want to run the fuzzers that you already wrote, right? And you dedicated time to writing those fuzz tests every time you push new code. But we have new challenges with fuzz testing because unlike unit tests, which are quick, hopefully, fuzzing can run indefinitely. So fuzzing, like I showed you before, is essentially infinite loop. So there is a question: how long should we fuzz our code? When should we stop the fuzz tests? What version should we fuzz? Usually, when we develop, we have like multiple branches. So do we have to fuzz on all branches? It will consume a lot of CPU power or like CI minutes in your CI provider. So those are the questions around the fuzzing workflow. And I'll talk about some of the workflows that I found effective from my experience. So when I started Fuzzit, I helped a lot of open source software to use fuzz testing and to run. Some of them actually already had fuzz tests, which is pretty cool. And I helped them to integrate fuzz testing into their CI/CD, and I'll talk about the workflows that I found to be pretty effective. So I helped, I think it was systemd, some CNCF projects. So some of them are C++ projects, some of them are Go projects, and there are essentially two workflows. The first workflow is the fuzzing workflow, which is essentially will help us find bugs as soon as new code is added. So for example, we usually fuzz one branch, or usually we fuzz the development branch, because really fuzzing every branch, if you have thousands of branches, is usually a bit an overkill. So really good rule of thumb is to think of either to choose one or two branches that you want to fuzz continuously, which are usually being updated frequently. So for example, a classic example or a simple example is if we have a development branches and where all the code is eventually pushed to the development branch, and some releases then are being made on some commits. So if we will take this case, every time what will happen is that every time we push new code to master, we build the fuzzers in the CI, in your CI, just like you build your tests. And then you upload those fuzz tests to another server where you will run your fuzz tests, because you don't want to run them in the CI, as it will really block your CI, because you want to run the fuzz test for hours or even maybe for days at the beginning, until either a timeout or until it finds a crash. And then so the fuzzer will run either until it finds a crash or until it gets a timeout that you decide, but this timeout can be actually even infinite, and or until a new version of the fuzzer is uploaded. So then usually, if you have frequent development, in the next day or even in the next few hours, there will be a new version. So what will happen? The new version of the fuzzer will replace the old version of the fuzzer. So the old version will stop running, and the new one will essentially start running from the same place, because we save the corpus, this test directory. So this is an important part. The test, you have to save the test directory between the runs. So you have to store it somewhere. and this way, the fuzzer is using this test directory as a seed corpus. It's called the seed corpus. So it's actually reusing all the knowledge from all the previous versions of the fuzzer. So this is one fuzzing workflow, and this essentially will help you to generate new test cases, a corpus directory. Also, it will help you generate find new crashes, right? And the second workflow, which I call a regression workflow, is a nice way of reusing all these test cases that were auto-generated to improve your. You can look at this as a way to improve your unit tests. So, for example, every time you open a pull request, you can download the corpus from your servers. And then you run libfuzzer has a way of running only the test cases that you pass to him. So it doesn't do any fuzzing; it's just doing regression. So you run the fuzzer through all the files that are available in the corpus. This is usually very quick, and you can do that inline in your CI. So this is really just like a free unit test, and it will help you both catch new bugs, and it will help you also catch bugs that, for example, you introduced again. So there is a crash that you already fixed, but now someone introduced the same crash. This workflow will help you catch this in a pull request before it's being merged. Yes, so this is some trophies of continuous fuzzing. So I think it shows why continuous fuzzing is actually an important piece in your CI if you use fuzz testing, of course. If you don't need to use fuzz testing, or you don't use it, then you can't use continuous fuzz testing. So on the left side, it was a project that actually had fuzz tests already, but it didn't run those fuzz tests for a long time. The code was a lot of code was added, and then you run the code, the fuzz test again, and found new bugs. So actually, those bugs probably would could be found pretty quickly if you run the fuzz test every time you push new code, and you see what code you can catch pretty quickly, what code caused it, and fix it before you release it to your users, as you run it usually on the development branch. On the right side, it's a project that it found the first bug after 10 hours. So if you really run your fuzz tests longer, and you should run your fuzz tests longer, not in your CI, then you will find probably new bugs. And this is really why fuzz testing is not a very good fit to the CI, or not a good fit, not a fit at all. Regression fuzz testing is a good fit. If you have a corpus, then you can run the fuzz tests through the test cases that are already generated, and the crashes that are already found and fixed, and find new crashes. One second. Yeah. So the future of fuzz testing, I think there is a lot of there's relatively a lot of work that is being done on improving fuzz testing. One important aspect is structure-aware fuzzing. So currently, LeafFuzzer supports generating just byte arrays. It doesn't mean, even now, it doesn't mean that you can only use fuzz testing on software that is on function that only gets byte array. You can do some simple work of transforming this byte array to the structure that you need, to the structure that your functions or the software expects, and it will work. Yeah, so LeafFuzzer is smart enough to go through the code, through the additional code, transformation code that you wrote, and should work. And there is no should be no issue with that. But the work that is being done is actually to support structure-aware fuzzing out of the box for LeafFuzzer. So, for example, you will have the ability to get like other things, and not just byte arrays. So, just looking to see if there are any questions. Right. Yeah. So no questions for now. Yeah. So I'll do a short demo of. Okay. Before that, another thing about the continuous fuzzing. So I'll go to the workflows for one more second. So there are a couple of options implementing this in your CI. So you either can do that yourself if you have enough capability, but I think it's relatively a lot of work of putting the fuzzers in the server, running them, saving, maintaining the corpus. So there is an open source solution. It's called Cluster Fuzz. So it's a hosted solution. You can run it in your cloud. I think it's quite dependent on GCP, but it will run in your GCP account. There is some work to. I think there is some work that they're trying to do to disconnect it from GCP, but as far as I know, currently it's connected to GCP account. But Cluster Fuzz will I think is currently the de facto standard open source solution to use if you want to self-host continuous fuzzing solution. So this is, I think, a good way to do it if you have the time to really self-host it. But it should be, I think, much better than really re-implementing some of the stuff that is already implemented in Cluster Fuzz. So it kind of does all the things that I talked about in the workflow. Other things, there is, so I worked on a managed solution in Fuzzit, and now it was acquired by GitLab. So it will be available. I think it will be available in a few months in a beta. I don't know the exact dates yet because I just joined, but I believe it will be available in a beta in a few months in GitLab. So of course, if you're a GitLab user, you should have access to it. I believe it will be in the Ultimate package for GitLab, but again, I'm not the product manager for this, So I'm not sure about this, but it will be announced. I have one question, 1 second. Yeah, okay, so I have a question here. So the question is, on one of the slides, it was written that it took 10 plus hours to find a bug. How long how long usually in commercial products it takes to fuzz testing, and or what is like the best practice of how long should you fuzz? So yeah, so it's a good question. So in the workflow that I showed, really, if you have the resources, usually you can, yeah. So okay, I'll answer this question a bit differently. So in every project, the number of fuzz tests is usually not that big because unlike unit tests, fuzz testing is so unlike unit tests where you have a lot of unit tests. In fuzz testing, you usually find function or a number of functions that are, like the main functions of some functionality, and you write fuzz tests for them. So you have, let's say, 3, 4 fuzz tests, and you can run them indefinitely. It's not usually very big resource consumption to run for fuzz tests indefinitely, but actually you're not running them indefinitely, because if you have if you have a repository which is actively being developed, you actually swap new versions very frequently. So there is always one version that is being fuzzed indefinitely, but it's always the latest version. So like the answer is there is always, every fuzz target can be ran indefinitely, but it will be swapped with the latest version every time you push new code. So 10 hours is not a lot. I think, and yeah, so I'll share my screen in a second. So before that, another example about the question. There is another famous solution, I think, OSS fuzz, which is for like it's a managed cluster fuzz or managed continuous fuzzing solution for open source projects, and they have the same. Also, I believe they use the same workflow. They fuzz the latest versions like probably indefinitely, and they just swap new versions. So now I'll share my screen. Yeah. So here really it's a preview of the GitLab capability which will be available. It's a Go project, but it really doesn't matter because it will be you'll have kind of the same behavior in the UI. So if we'll go to our CI YAML, so what you will have to do. Yeah. So I increased the font a bit. Hopefully you will see better now. So what you need to do to be able to use the continuous fuzzing in GitLab, you need to include template which is available in the GitLab product, coverage fuzzing. And then there is another stage that you have to add, fuzz stage, just after unit tests. And for every fuzz target, you introduce a new step, fuzz test. In our case, it's fuzz test parse complex. If you have another function, you just add another step. And then, so this is, you can ignore this. In our case, it will be just clang. Okay, you compile the fuzz target, just like you compile your any lib fuzzer targets with fsanitize, and then you need to run this the binary with something called glfuzz. It will be available in the step, and this will actually already take care of all the workflows that that I showed in the slides, and now you will be able to see how it looks in the CI. So the fuzz, every time you push new code to master, in this case, you will have a fuzz step that will run asynchronously, so it will not block your CI, but if it finds the crash, you will get notified about the crash. And of course, you can see like the output and the crash that it found, like the backtrace and standard libfuzzer output in the logs. But you will be able to download the test cases, so you will have the crashes here. You will be able to reproduce it, and also we are doing some additional analysis and parsing. So you will be able to see the additional analysis here. So in that example, it's index out of French. Index out of French in C++ example, it will be heap overflow. So you will have a crash state. You will be able to download and reproduce it. And a regression workflow, this will be in line in the CI. So for example, I opened a pull request, and what happened in that case, first I fixed the crashes, and you can see here that it downloaded all the test cases that were generated by previous runs and ran them through my fuzz target. So now I got more tests, and actually good tests, because those are only tests that get us to additional coverage. And so yeah, everything here was successful. And yeah, so that's the regression. So this is really free, nice way of additional free unit tests and regression.
All right, Evgeny. I have a question myself. So since the acquisition of Founded by the GitLab, are there any plans of integrating in any other CI/CD services like, I don't know, DMCT or GitHub Actions?
Yeah, so I don't believe so. So I'm really, it's really happened, I think 2 weeks ago. So when it was planned in April, I was still in the Fuzzit. But so Fuzzit was available in other CIs, but I think this will be only available in GitLab. I think Cluster Fuzz is an open source solution, so you can implement. Cluster Fuzz works with any CI, so you just have to manage the instance. So Cluster Fuzz is essentially where you save. It takes care of saving the corpus there, but you add all the steps in your CI that you already use. Travis, Circle CI, whatever team city, and you just send the corpus to the cluster fuzz URL, and it's being run there.
All right. And I have questions about the corpus, the way it mutates and gets generated. So do they get seeded with different seeds for random generation every time, or do they repeat itself, like use the same seed every time, or it's maybe tweakable?
Yes. So I think so I forgot maybe to mention it. A good way of improving the fuzzing process is also providing something called seed corpus. It can also start with empty seed corpus, right? But if you have already examples of like correct examples, so if you have a JSON parser, if you have correct examples of JSON, it will help the fuzzer advance quickly and find bugs quicker than just taking all the time to generate very basic examples himself. So usually you give it also a seed corpus. So it's another directory with correct test cases. And then it generates just a new directory, the corpus. So there is the seed corpus, which is the corpus that you give it as a seed input. And there is the corpus which is being generated by the fuzzer while it's being ran. And then, of course, if you run it again, you just pass it, like your seed corpus essentially just grows bigger because you pass the live fuzzer target you can pass it multiple directories. So it essentially starts from both the seed corpus and both the corpus that was generated by previous run. Yeah.
All right. And does corpus generator, to say it, teach itself on what data was more successful in ways of breaking actually the program, and maybe like adding some of the corpus data to a like extra VIP status that it would be prioritize it higher in the continuous integration and continuous runs for new pull requests.
So can you maybe repeat it? I'm not sure.
For example, that we have few, I don't know, data sets that breaks pretty constantly our program, and after every single run, does the fuzzy prioritize these data higher and runs it in the first place because it knows that similar data was breaking the I don't know, the program more often?
Yeah. So I don't think usually like live fuzzer prioritize anything. I think the important thing is just to pass it all the previous data that were generated, and then it just takes it from there randomly. And usually, if there is an additional crash that really breaks the program, often, like you said, I believe it should find it with his general algorithm. There is no priority feature, as far as I know, in the current implementation.
Right. So we have a question in Telegram chat. So what you may say about fuzzing the std regex?
So I think it's a good library to fuzz. I believe someone already did it because it's really standard library. So yeah, if there is a bug there, it's a serious bug. But if someone, I believe you can look on the internet. If no one did it, then I guess it will be interesting, very interesting library to fuzz.
I get it. Do you have maybe a rule of thumb on how long a single pass, not like the whole session, but single pass for fuzzy test would run? As for example, when working on H.264 codecs, one single pass for the codecs as a black box could take us up to 2 days due to a lot of terabytes of video passing, just to make it constant. So, and heck, I guess having single pass with a little mutation is not really beneficial. So, like, how long should it run? For example, a single one.
Yeah. So that's a good question. A rule of thumb is that a single pass should be as quick as possible. So the seed corpus that you provide, you should contain it should contain it's called minimized examples. So the smallest possible examples that gets to more code coverage. So for example, if we have I don't know JSON parser, then if you just add a lot of so the smallest possible examples, but also like different examples. So because every iteration should be as quick as possible, otherwise the fuzzer is not effective. And usually it's possible because usually you can get to the same functionality with a smaller piece of input, and not only with long video or whatever long piece of data. You can sometimes get to the same functionality in the software with very small piece of data.
All right, that makes sense. And as for the mutators of corpus data, are there ways to add custom mutators that are specifically designed for some data?
Yeah, I think it's possible in libfuzzer. There is I think it's part of the structure aware fuzzing. I think it's also possible to add your own mutators to that. It's a bit an advanced topic because it will require a bit more engineering and development.
I see. So far, no questions for the chat as I see in Zoom and Telegram. So we can continue to talk to each other. Also more questions.
I have I can also mention another thing about fuzzing, maybe a question that I had in some time. So, or I think question that someone asked me is that, okay, so for example, if my product is not open source, right? And then I release the software, so how someone is available to fuzz my software, right? And find bugs, because I don't release the software, and libfuzzer works with the only with the source code, right? So because it needs coverage guided feedback. So there are also options to, it's called black box fuzzing. So it's not relevant for developers, but this is just to explain why it's possible also for a malicious user, right, or for a hacker to fuzz your software even if the source is not available. For example, AFL has a plugin or a feature to run it with QEMU. So it just instruments the instruction at the instruction level. It's much slower. So as a developer, you have the advantage that your fuzzers will run much faster and will find the bugs much faster than the hacker will do. But still, it's possible to run the same AFL algorithm on black box software with it's called QEMU plugins.
I guess have like more around 5 minutes and last couple questions. So are there plans to have, I don't know, some GUI testing apart from Slang and Stacking API, but maybe like box, or maybe, you know, like how do people test mobile applications? We use two servers, and one of them like run an application and others just send some random data to operate with GUI and UI and other actions. So are any plans on this kind of stuff?
Yeah, so I think, yeah, definitely API fuzzing is a new, I would say, like, relatively, maybe I would say it's a new topic, but yeah, it's an interesting topic. There are challenges in API fuzzing because you don't have the coverage feedback, which proved to be very effective. But so API fuzzing is a bit of different algorithm and different engine, so it's not connected to libfuzzer. But there are like fuzzers like Zap proxy for API and Peach fuzzer. I think it was also acquired by GitLab now. So I think some of that also should be open source, I believe, in some stage. I'm not sure. So there are API fuzzers, but they work more like they work more with generational and random algorithm than coverage guided. But sometimes it can still be effective because they use like they use some magic, you know, they reuse some magic heuristics or like heuristics and some data that they know leads a lot of time to crashes. A very popular SQL fuzzer is I think SQL map. So if you have a SQL query in an API, SQL map I think found a lot of bugs, but some of those tools are usually more used at by more manual research, more manual work, security research or developer, you know, trying to just find new bugs in his software or like auditing other software. I didn't see it a lot with integrating into the CI yet, but Zap proxy and I think GitLab as well is working on some of that direction.
Thank you very much. We have a time running out. Yes, thank you for such a great speak. Yes, if you have another questions, you may go to the Zoom discussion. Yes, and we have this meeting room. Link you can have in the chat. Yes, and thank you again for a great speech.